So this time we want to characterize the linear independence of a set containing 3 vectors. But the set is parameterized by a real number. Now, for that, in order to continue, we need to recall a few things. The first one is that a set of vectors v1, v2, up to vn, all of them column vectors with the same number of entries, is linearly independent if whenever we observe this equation, well, that implies that all the coefficients of that equation are 0. Now, how do we use this to test the independence or dependency of our set? Well, we start like this. Let A, B, and C be real numbers. Those are going to be our coefficients. What we're going to do is assume that the equation that we have here actually takes place. Well, this one denotes, of course, the 0 column vector. Okay, now what happens with this vector equation, this matrix equation? Well, is that this one induces a system of linear equations. Which one? Well, the one that I'm going to describe. A plus 3b plus 5c is equal to 0. A plus 2c is equal to 0. A plus 2b plus c times x plus 3 is equal to 0. Of course, this can be converted into an augmented matrix representing the system of equations. It's not a surprise that we're going to just borrow the columns that we have here, right? So it's going to look like 1, 1, 1, 3, 0, 2, 5, 2, x plus 3, then the augmented portion, 0, 0, 0. Now each of the columns have a meaning. This one corresponds to the coefficient associated with A, with B, with C, and this one the constant that comes on the right side. Okay. Well, time for the reduction process. We're going to do 2 steps, 2 reductions in a single step, but we'll get it from there. So to row 1, I'm going to subtract, to row 2, I'm going to subtract row 1, and to row 3, I'm going to subtract row 1. That is already signifying that I'm going to take this as a pivot and then just get rid of this ones, right? To process that column. And the result of that operation is the following. I have 1, 3, 5 as the first row remains intact. Now I have a 0. For this one I have 0, negative 3, and negative 3. And well, for the second, for 0 here, then I have 0, negative 1, x minus 2, and I have 0 here. Okay, well, next operation. Now I'm going to turn, I'm done with the first column, so I move to the second column. I select this as the one that's going to be my pivot. So I'll take, I'm just doing regular row reduction. So negative 1/3 of row number 2 will make the following conversion. It would be 1, 3, 5, 0, 0, 1, 1, 0, and then, okay, of course, the third row remains intact, so 0, negative 1, x minus 2, 0. Now from here, well, now this is my pivot. I'm going to use it to kill this and to kill that. Okay, to process the second column. So we'll do it, 2 operations. To row number 1, we subtract 3 times row number 2. To row number 3, we add row number 2. Now, the result of that operation is the following matrix. 1, 0, 2, 0, 0, 1, 1, as that one remains intact. And now 0, 0, x minus 1, 0. Well, Now time to interpret things. Because now we arrive to this point where we have our parameter. Two possibilities. Either x minus 1 is 0 or is not. Let's examine the later first. Case number 1. We have x minus 1 is different from 0. Well, in that case, the reduction process is going to continue in this fashion. Just multiply row number 3 by the reciprocal of x minus 1. That will turn into 1, 0, 2, 0, 1, 1, 0, 0 over here, 0, 0, 1, 0. What is that telling us? Well, that now I can use this as my pivot and get rid of these ones. What would that imply? Well, use the following operations to do it. To row 1, subtract twice row 3, and to row 2, subtract just one time row 3. The resulting matrix looks like this: 1, 0, 0, 0, 1, 0, 0, 0, 1, and then 0, 0, 0. What is that telling us in terms of the coefficients a, b, and c? Of course, let's not forget what the meaning of these columns is. Right? We just recover it. But that is a system of equations. The system says that a is 0, b is 0, and c is 0. So under the presence of the condition that x minus 1 is different from 0, well, we get linear independence of the set. What about the other case? When x minus 1 is 0, well, the resulting matrix, right, that we had from here, from this point, looks like this: 1, 0, 2, 0, 1, 1, 0, 0, 0. And what can we say? Well, in this case, it's not difficult to verify that this is indeed the end of the row reduction process. There's nothing else that we can do. Well, if we're done with that, let's recover the system of equations. Right? The system of equations indicates that a plus 2c is equal to 0 from this one, and that b plus c is equal to 0. In other words, we can put a and b in terms of c. Equivalently to the system of equations, we have a is equal to negative 2c and b is equal to negative c. So, if for instance I set c to be negative 1, I get that a is equal to 2 and b is equal to 1. So what I get is a non-trivial solution to this equation. In other words, having this doesn't imply that all the coefficients are 0. Namely, the system of equation, the set of vectors that we have is linearly dependent. But that depends only on the value of x. In other words, the set is linearly independent if and only if, well, x is different from 1. And with this we conclude.